To build the perfect machine, you want absolute obedience. An actuator must track a trajectory without deviation, instantly correcting if a heavy weight drops. But in the physical world, every automated system is fought over by three competing signals. There is the command reference telling the machine what to do. There are external disturbances, physical impacts, friction, and wind, trying to push it off course. And there is sensor measurement noise, electrical static feeding false data back into the system's computers. The control loop takes the difference between the desired command and the actual measured output to calculate an error signal. The primary objective of the controller is to calculate a correction that drives this error signal to absolute zero. For decades, mid-century draftsmen and classical engineers operated under a straightforward assumption. If a machine couldn't perfectly eliminate this error, the hardware was flawed or the controller wasn't tuned aggressively enough. This pursuit of an error-free machine ignores a fundamental barrier. The dream of perfect isolation is expressly forbidden by the laws of mathematics. Control engineers do not actually eliminate error. They are only permitted to move it around. This diagram maps the standard feedback loop architecture. You have the plant, the physical machine, and the controller governing it, along with distinct injection points for the reference command, the disturbance, and the noise. External physical disturbances enter the system at the plant's output. Conversely, electrical sensor noise enters at the feedback measurement point on the opposite side of the loop. The system processes these inputs through two mathematical filters. The output sensitivity function, denoted as S, dictates how the system reacts to physical disturbances. The complementary sensitivity function, T, dictates how it reacts to sensor noise. These two filters are bound by a rigid algebraic constraint. S plus T always equals the identity matrix, or simply 1, at any given frequency. If you tune the controller to shrink S towards 0, T is mathematically forced to expand toward 1. Because of this equation, a system designed to be perfectly stiff against physical bumps is mathematically guaranteed to hyperreact to its own sensor static. To see how this plays out, engineers evaluate error over time, looking specifically at how a machine behaves as it settles into a steady state. Using the final value theorem, they calculate the exact difference between the command input and the machine's output in the limit as time approaches infinity. This brings in the concept of system types, labeled type 0, I, or II. These classifications are based entirely on the number of pure integrators present in the forward path of the feedback loop. An integrator accumulates the history of the error over time. By incorporating this integration, like the I component in a PID controller, the system is forced to continuously correct itself until the steady-state error for a constant step input drops to 0. This is a time domain plot of a step response. When the integrator is added, it pulls the trailing error line perfectly flat, neutralizing the constant command error over a long enough timeline. But reaching 0 error at infinity does not protect the machine in the present. It ignores the violent, chaotic transient oscillations that occur before settling. To guarantee true stability, the analytical perspective has to shift. We must stop looking at error over a timeline of seconds and start analyzing how the system responds to continuous vibrations across the frequency spectrum. Fixing error at steady state is merely a localized repair applied to a single point in time. Real system robustness requires the machine to survive the entire frequency spectrum. In the frequency domain, the output sensitivity function, S, acts as the shield against low-frequency physical disturbances, like sustained wind shear or constant mechanical friction. To reject these low-frequency disturbances, the math demands that the controller output a massive open-loop gain. On the other end of the spectrum, the complementary sensitivity function, T, acts as the shield against high-frequency measurement noise, like electromagnetic static pulsing through a sensor. To reject this high-frequency noise, the math demands the exact opposite, a microscopically small loop gain. A system cannot maintain a massive gain and a microscopic gain at the same frequency. The requirements are mutually exclusive. This is a logarithmic Bode plot mapping the S plus T equals 1 constraint. If you push the S curve deep down into a valley to improve tracking at low speeds, the T curve is forced up to a peak, destroying stability at high speeds. This trade-off is restricted by permanent geometric flaws built into the physical architecture of certain plants, such as a 0 locked directly at the origin of the complex frequency S-plane. Such a 0 is a fixed mathematical coordinate. The controller cannot bypass or erase it. According to the maximum modulus principle, the sensitivity at this exact coordinate is mathematically locked to a value of 1, preventing any disturbance attenuation whatsoever. The system's own physical geometry prevents engineers from uniformly shielding the machine from all disturbances. The ultimate proof of this limitation comes from Cauchy's theorem in complex analysis. In engineering, it translates into a strict law known as Bode's integral. Bode's integral dictates that for any standard system, the total integrated area of the log sensitivity curve across all frequencies is a fixed mathematical constant. This establishes a literal conservation law for error. Just as physicists recognize the conservation of mass or energy, control engineers must account for a finite, conserved volume of instability. Known as the waterbed effect, the shaded area beneath this curve represents the system's fixed volume of error. If the controller presses down the low-frequency curve to reject physical bumps, the high-frequency side violently bulges upwards. The exact same total area is always preserved. A control engineer does not destroy error. They merely squeeze it out of the operating frequencies and hide it in the high-frequency regions, gambling that the machine won't vibrate fast enough to feel it. To see how these abstract theorems govern heavy physical stakes, we can look at the control of a high-performance industrial robotic arm. The arm is driven by a DC motor. The electrical armature circuit, the rotor's inertia, and its viscous damping provide the raw electromechanical constraints the controller must shape. Under the classical PID approach, an engineer manually adjusts proportional, integral, and derivative gains to dictate exactly how the arm moves towards its target. But increasing the gains to force the arm to move faster, decreasing its rise time, almost always causes it to overshoot the target position. This overshoot is directly connected to the waterbed effect. The arm swinging past its target is the physical manifestation of that high-frequency error bulge. Modern control theory offers the state space framework and the linear quadratic regulator, or LQR, as an automated alternative to this manual PID tuning. LQR solves the algebraic Riccati equation to find the mathematical optimum between two competing penalties, the Q matrix, which penalizes state error, and the R matrix, which penalizes the expenditure of control energy. By adjusting these penalty matrices, the engineer directly changes the physical behavior of the robotic arm, forcing it to prioritize either absolute precision or strict energy efficiency. Whether manually tuning a PID loop or computing optimal matrices for LQR, the engineer is simply choosing exactly where in the system they are willing to suffer the inescapable error. The ultimate goal of loop shaping is to sculpt the open loop gain to perfectly counter the specific environment the machine will live in. The ideal shape forces the sensitivity function down at low frequencies, where physical bumps live, and pulls the complementary sensitivity function down at high frequencies, where sensor static dominates. Ultimately, control engineering is a high-stakes negotiation, requiring the engineer to trade one form of instability for another. The mathematical laws of the universe cannot be broken, but they can be carefully navigated to keep a system safe. Control theory finds its utility in the geometry of compromise, enabling flawed machines to maintain stability in a world defined by noise and chaos.